Hello everyone, a very good afternoon. Myself Kumari, Industry Relationship Coordinator at Takshila VLSI Technologies. Welcome to today's VLSI webinar. Before we start, I would like to give a brief introduction about our institute. We Takshila Institute is a leading VLSI training center in Bangalore and Hyderabad. We offer special courses, helps you learn important skills in the VLSI field. We offer physical design, analog layout design, analog circuit design, ASIC verification, and design for tests. Why to choose Takshila? Here are some of our unique features. We provide 24 by 7 tool access and VPN support for continuous practice. Hard copy materials are provided to enhance your learning experience. Experienced trainers. Our trainers have over 10 plus years of industry experience. Placement support. We offer 100% placement assistance until you secure a job in the VLSA or semiconductor industry. Our candidates have successfully secured positions with leading companies such as Micron, Synopsys, Intel, InSemi, OnSemi, Wipro, etc. Today's webinar will be presented by Rohini ma'am. Ma'am have over 5 plus years of industry experience and currently works as a physical design engineer. Now I'll hand over the session to Rohini ma'am to continue the webinar. Thank you.
Hello everyone, good afternoon. I am Rohini, currently working as a physical design engineer in a very well-known company with over 5 years of the experience in VLSI industry. I have worked on various stages of the physical design flow like floor planning, placement, CTS, routing and timing closure using the industrial standard tools such as ICC2, ICC, Prime Time and DC Compiler. I am also mentor at Takshila Institute where I support the students to understand the basics and guide them towards the careers in semiconductor field. In today's session, I will be taking you through the topic webinar on VLSI semiconductor industry. So let's get started. So first one will be the agenda. So these are the topics which I am covering in today's webinar. So in that, the first one will be the VLSI or semiconductor industry introduction. So here I will discuss what is the meaning of VLSI industry, growth for the VLSI industry and scope for the VLSI industry. After that, I will discuss eligibility criteria for VLSI jobs. So to get a job in VLSI, so what are the qualifications are required? I will discuss here. About Takshila VLSI, courses offered and unique features, core job opportunities, industrial salary scope, placement at Takshila VLSI. After that, I will discuss some technical part of today's webinar. So it includes AMS and customized layout design flow, ASIC or chip design flow, RTL design and verification concept, physical design flow, and lastly I will discuss some question and answer session. So if you have any questions means you can ask here. So next one will be the terminology. So these are few words which we are using in our entire VLSI industry. So you may heard these words like semiconductor, VLSI, chip or ASIC. So you already heard about these words. So in that, the first one will be the semiconductor. So you already know what is meant by semiconductor. Semiconductor means the material whose conductivity is lies in between conductors and insulators are called as semiconductors. So next one will be the VLSI, means very large scale integration. So in very large scale integration, we are using some billion of the transistors in one IC. So before this VLSI, we are having another generations like small scale integration, medium scale integration, and large scale integration. So in small scale integration, we are using some thousand of the transistors in one IC. In medium scale integration, we are using some 10,000 of the transistors in one IC. In large scale integration, we are using some million of the transistors in one IC. So in very large scale integration, we are using some billion of the transistors in one IC. So chip or IC are also called as integrated circuit. So you may ask question, why we are calling it as integrated circuit? Because so whatever the transistors I am calling, so that all transistors are integrated in one circuit only. So because of that purpose, we are calling it as integrated circuit. So ASIC means application specific integrated circuit. So what is meant by application specific integrated circuit means, so whatever the ICs we are using, so that will be used for specific application purpose only. We cannot use it for the another applications. For example, you can take if you are using your mobile phone, so that will be used for the specific application purpose only. So your mobile phone can't be used for the another applications like automobiles and all. So whatever the ICs we are fabricating, so that will be used for specific application purpose only. So that will be called as ASIC here. So where the chip or ICs are used. So in our day-to-day life, we are using lot of the electronic equipments. So in that all we are using the ICs here. So for example, you can take in your mobile phone also you are using some ICs. So in your laptop, TV, satellite, cars, and even in a small calculators also we are using the ICs here. Then how a chip interior look like? So whatever the image you are seeing on the screen, so this will be the image of the chip. So whatever the black color portion you are seeing, so this will be the black color portion. So whatever the black color portion you are seeing, so this will be called as plastic package. So you may ask question, why we need this plastic package? So what is the need of this plastic package then? So we'll require this plastic package to protect our IC. Then how this plastic package will protect our IC? So it will protect our IC from the external sources like moisture and temperature. So if any environment condition will changes in external environment, then it will protect our IC. From the damaging, it will protect our IC. So for that purpose, we are using this plastic package. So inside this plastic package only, semiconductor die or IC will be present. So this will be the IC, or also called as semiconductor die. So whatever the input and output of the ICs are there, so that will be connected to gold bond wires. So these are the gold bond wires. So you may ask question, why we are using only gold here? Because gold has more conductivity rather than another conducting material. So because of that reason, we are using gold here rather than another conducting material. So it is also recommended that we are not directly connecting these gold bond wires to external circuits, because if any fluctuations happen in external circuit, like any current fluctuations or any voltage fluctuations will happen in external circuit, then it will directly damage your IC. So first we will connect these gold bond wires to external pins, and these external pins will connect it to the external circuits. So whatever the size of the chip will be there, so that will be 5 mm into 5 mm here. So next one be the semiconductor wafer. So this will be the image of the semiconductor wafer. So whatever the ICs I am calling, so that all ICs are fabricated on this semiconductor wafer only. Then what is the meaning of semiconductor wafer then? Semiconductor wafer means Basically, it is a silicon material die on which number of the ICs are fabricated. So all the ICs are fabricated at the same time for the different applications here. For example, you can take, so whatever the square like structure you are seeing, this will be called as one IC. So like this only, the number of the ICs are fabricated at the same time for the different applications. Means one IC will be used for mobile phones, IC will be used for laptop. So for the different applications, we are fabricating all the ICs on a single semiconductor wafer here. So after fabrication of the all the ICs, according to the size of the ICs, we will cut this wafer. So we'll cut this wafer according to size of the ICs. Then we will take that ICs and we will pack that ICs and we will supply that ICs. So this process will be there in this semiconductor wafer. So whatever the wafer size will be there here, so that will be 12-inch wafer. So, how many chips are integrated? So, in 1970, means when ICs are invented, at that time, only 5,000 transistors were integrated. Means we are used only 5,000 transistors in one IC. So, today 100 billion of the transistors or MOSFETs are integrated. So, nowadays in industry, we are using more than this of 100 billion of the transistors or MOSFETs in one IC. So this will be the MOSFET structure. So you already know the functionality and operation of this MOSFET structure. So by using this MOSFET structure only, we are fabricating the ICs here. So VLSI introduction Moore's law. So whenever you are start studying about the VLSI, first thing you should know about the Moore's law. Then what is the meaning of Moore's law then? Moore's law means it is the observation that the number of the transistors in a dense integrated circuit doubles about every 2 years. So the observation is named after Gordon Moore, the co-founder of the Fairchild Semiconductor. So what is the meaning of this means? So whatever the transistors we are using in one IC, so that will be doubled after 2 years. Means, for example, you can take, if you are using 4 transistors in this year, after 2 years, the number of the transistors used in one IC, that will be doubled. Means it will be doubled from 4 transistors to 8 transistors here. So you can observe in this graph. So in 1970, the number of the transistors used by this Intel 8008 chip will be 5000. So after 2 years, means in 1972, the number of the transistors used by this Intel 8008 chip will be 10,000. So this will be doubled from 5,000 to 10,000 here. So you can observe here in 2018, the number of the transistors used in one IC will be 50 billion. So we are used 50 billion transistors in one IC. So like this only, for every 2 years, we are increasing the number of the transistors in one IC. So nowadays also in industry, we are following this Moore's law. Nowadays also we are increasing the number of the transistors in one IC for every 2 years. So this is all about the Moore's law. Then how we are increasing the number of the transistors in one particular circuit. So integration made it possible. So technology is enabling us to reduce the size of the each transistors or MOSFET. So however the technology is improving, we are reducing the size of the transistors or MOSFET. Then how we are reducing the size of the transistors or MOSFET? By using the technique called as MOSFET scaling. So what is the meaning of MOSFET scaling then? So MOSFET scaling means it is the technique where we are reducing the size of the transistors or MOSFETs based on the voltage or current. So based on the current and voltage, we are reducing the size of the MOSFET or transistors by using this MOSFET scaling technology. So you can take example here. In 1971, the size of the transistor will be 10 micrometer. So in 1987, by using this MOSFET scaling technology, we are reducing the size of the transistor as 800 nanometer. So we have scaled the transistor size from micrometer to nanometer here. Means this nanometer is even smaller than this macrometer. You can observe here 1 micrometer is equal to 1 millionth of the meter and 1 nanometer is equal to 1 billionth of the meter. So this nanometer is even smaller than this macrometer, and you can observe such a small transistors were used in 1987. So like this only for every 2 to 3 years, we are reducing the size of the transistors by using MOSFET scaling technology here. So in 2022, we have reduced the size of this transistor as 3 nanometer. In 2024, we have reduced the size of the transistor as 2 nanometer. So nowadays in industry, we are using the size of the transistor as 1.8 nanometer. So in future, you may also use size of the transistor as 1.5 nanometer, 0.5 nanometer, and 0.1 nanometer as the size of the transistors. So what is technology node or tech node then? So whatever I am calling like nanometer, micrometer. So what is these all? So these all are called as tech nodes. So what is the meaning of that tech nodes then? So the size of the transistor in a chip is called as technology size. So whatever the size of the transistor is there, so that will be called as technology size. So what is the tech node then? Tech node means, so you already know the transistor diagram. This transistor diagram consisting of some source, some drain, and some gate. So whenever you apply voltage to this drain, channel will be created and electrons will start flowing. So whatever the distance is there in between the source and drain, so that will be called as tech node. So that will be called as tech node here. So typically tech nodes used in a production. So whatever the tech nodes we have used, so that are 28 nm, 32 nm, 45 nm, 65 nm and 90 nm. So these all distance like 28, 32. So this will be the distance between this source and drain here. So these all tech nodes use the MOSFET technology. So any size, so which is lower than this 28 nm. So any size which is lower than this 28 nm will use this FinFET tech node. So you may ask question, what is the meaning of this FinFET? FinFET means, so whatever the gate will be there, so that will be divided as number of the circuits, and whatever the direction of the current will be there, so that will be multiple direction here. So because of that, it is having some advantages like less power, means less power consumption, then less area utilization, and less cost. So because of these advantages, we are using this FinFET tech node rather than this MOSFET technology nowadays in industry. So the size which is lower than this 28 nm, like 3 nm, 5 nm, 7 nm, 14 nm, which are lower than this 28 nm. So these all tech nodes use this FinFET tech node. So this is all about the technology node and tech node. So semiconductor industry demand drivers. Semiconductor demand by end market. So this will be the percentage wise distribution where we are using the more ICs and which industry will be increasing its demand. So in computing stage, we are using some 34% of the ICs. So in wireless communication, we are using some 30% of the ICs. In consumers, means in laptops and mobile phones, we are using some 14% of the ICs. In autos, we are using 8% of the ICs. In industrial, so in industrial, we are using lot of the automatic machines. So in that all we are using the ICs. So we are using some 8% of the ICs in industrial. In wired communication, we are using 5% of the ICs. So even in military and aerospace also, we are using some 1% of the ICs. So this is all about the semiconductor industry demand drivers. So VLSI or semiconductor industry growth. For every year, the growth of the semiconductor industry will be 8.6 percentage. So this will be the compound annual growth rate of the semiconductor industry. So you can observe in this graph, in 2023, the growth of the semiconductor industry will be $544.78 billion. So in 2024, the growth of the semiconductor industry will be $584.17 billion. After 10 years, means in 2033, the growth of the semiconductor industry will be $1,137.57 billion. So you can observe here, for every from year to year, the growth of the semiconductor industry will be increasing and opportunities also increasing here. So next one will be the VLSI or semiconductor companies. So whatever the VLSI or semiconductor companies are there, so that will be broadly classified as product based companies, EDA companies and service based companies. So these product based companies will do the project and the fabrication. So these EDA companies will provide the tools. Tools means softwares. So which is required to do the project. So that tools will be provided by these EDA companies. So service based companies. So as the name suggests, it will provide the service to these EDA companies and product based companies. So these EDA product and service based companies will always be in sync up to meet the technology deliverables with the support of the VLSI engineers. So if any one company is not there, then VLSI project will not be completed here. So semiconductor industry ecosystem. So whatever the semiconductor ecosystem is there, so that will be broadly classified based on the work and performance by the companies. For example, you can take fabless chip firms. So you may ask question, what is meant by fabless? Fabless means whatever the fabrication process is there, so that is not present in these companies. So whatever the project will be there, so that will be completed without using any fabrication process here. For example, you can take AMD, Qualcomm, MediaTek, Marvell, Broadcom, Media. So in these all companies, so whatever the fabrication process is there, so that will be not present here. The foundries. So whatever the project we are doing, so that almost all project will be fabricated in this foundries itself. So the foundries like Global Foundries, TSMC, Samsung, SMIC, UMC. So these all foundries are there in this foundries and fabless non-chip firms. So the software companies like Apple, Google, IBM, Meta, Amazon. So these all software companies are there in these fabless non-chip firms. So you may ask question, these are the software companies where we are using the VLSI industry. So at the stage of the computing, means at the stage of the data server and at the stage of the web server, we are using these fabless non-chip firms. So IP and design software. So to do the project, we will require the tools. So that all tools will be provided by these companies like Synopsys, Siemens, Anais, ARM and Cadence. So these all companies will provide the tools to do the project here. So to do the project, we will require the equipments. So that all equipment will be provided by the companies like KLA plus ASML, Tokyo Electron, Lam Research and Applied Material. So these all companies will provide the tools, provide the equipment to do the project here. So integrated device manufacturers. So the companies like Texas Instrument, Analog Devices, Micron, Intel, Samsung. So these all companies will be there in this integrated device manufacturers. So after the fabrication of the ICs, we will need to test that IC and we should pack that IC and we should supply that IC. So for that purpose only we are having some companies like TER, Amcor, Agilent, Lattice and Foxconn. So these all companies are there in this testing, packaging and assembly. So this is all about the semiconductor ecosystem. So top semiconductor product based companies. So in 2023, the revenue of the semiconductor industry will be $545 billion. So in that, Intel itself 9.4 percentage and Nvidia triple its share at the end of year. So Nvidia has some 9 percentage of the revenue. So the companies like Samsung, Qualcomm, Broadcom, AMD, Infineon, Texas Instrument, NXP, Sony, onsemi. So these all companies are there in this top semiconductor product based companies. So next one will be the ED or CAD companies. So I already told these ED or CAD companies will provide the tools. So these provide the tools to the project here. So you may ask question, what is the meaning of tools there? Tools means it is a software. So it is a software which is used while designing the chip. So whenever we are designing the chip, we will require this software or tools. So EDA means electronic design automation. Then why we require this EDA tool then? So whenever we are designing the IC, for IC design, so we are using this EDA software, means EDA tool. So CAD means computer aided design. So why we require this CAD tool then? So whatever the ICs we are fabricating, so that will be observed in 2D and 3D form. So that is needed to observe in 2D and 3D form. So because of that purpose, we are using this CAD tool. So every step. So to make one IC, so it will take some different steps. For different step, we are using different tools here. For example, whatever the synopsis company is there, so that will be uses ICC2 tool for the IC design. So whatever this cadence company is there, so that will uses Innovus tool. So that will be uses Innovus tool for the IC making. So whatever the IC verification will be there, so that will be performed by the tool called as Calibri tool. So whenever we are using this Calibri tool, so that will be used for IC verification. So these all tools will be used, so that all tools will be given by the companies like Cadence, Synops and Mental Graphics. So these all companies will provide the tools to do the project here. So next one will be the fab companies. So what is the meaning of fab companies means? So whatever the fabrication process is there, so that will be performed by these fab companies. So in that, The first one will be TSMC, means Taiwan Semiconductor Manufacturing Company. GF means Global Foundries. So these are the top foundries are there. These are the top fab companies are there in India. So every product-based company will have their own fabrication process, and some company will be complete their project without using any fabrication process. So we can take the example as Qualcomm. So in Qualcomm company, whatever the fabrication process is there, so that will be not present. So this is all about the fab companies and fabless companies. So top fabs worldwide, top 10 semiconductor foundries. So whatever the project we are doing, so that almost all project will be fabricating in this TSMC foundry itself. So this TSMC foundry is having the revenue of $16.7 billion. So it also includes some other foundries like UMC, Global Foundries, PSMC, SMIC, High, Samsung, DB. So these all foundries are there in this top fabs worldwide. So next one will be the 500 plus established VLSI companies. So I already discussed about product-based companies, ED or CAD companies. So next we will discuss about this VLSI service-based companies. So whatever the VLSI service-based companies are there, so that will be classified as MNC service-based, large service-based, and startup service-based. So the companies like Capgemini, L&T, HCL. So these all companies are there in this MNC service based. The companies like Mirafra, Insemi, Moship, Synop, Sankalp. So these all companies are there in this large service based. So the companies like Lux Semiconductor, Savitech, Bitsilva, Sinoff Semiconductor, Chris Semi. So these all companies are there in this startup service base. So along with these 500 plus more service based companies are there in Bangalore and Hyderabad location. So these all companies will hire the students and give the 6 months of the industrial training. After completion of that training, they will assign one project from the product-based companies or MNC-based companies. So after completion of that project, they will again assign another project from another MNC-based companies or product-based companies. So this process will be continued here. So we are having a small video on semiconductor IC making video. So after watching this video, we will get how the ICs are fabricated, how we will test that ICs, how we will pack that ICs, and how we will supply that ICs. So we'll see that one.
Memory chip design is the first step in the production of Micron's memory chips. This process involves the use of computer-aided design tools to lay out billions of electronic components that store data on the chip according to the product design specification. During technology development, specific process steps are defined and integrated into a process flow that will build the memory chips. The process steps are tested and refined until the process node is qualified and ramped in manufacturing. Individual memory chips, or die, are built upon pure silicon wafers in a fabrication area, or fab. Fabs are state-of-the-art clean rooms that are 100 times cleaner than a hospital operating room to ensure silicon wafers are protected from ambient contamination. Among the many process areas in a fab, the photolithography area coats wafers with a photoresistant material. Then, like film in a camera, circuit patterns are exposed and excess material is rinsed away. The paths in these circuits are 5,000 times narrower than a human hair. Wafers are moved between different tools and processes using a robotic automated material handling system, or AMHS. Each wafer may be moved through more than 1,000 processes. It takes more than 1 month to make a memory chip. In probe, initial functionality tests are performed on each die on the wafer. A probe card positions probe needles onto each die to send and receive test data. This information is used to generate a map of all the die on each wafer. Only good die that pass all tests in probe will continue through the manufacturing process. In assembly, wafers are first thinned, attached to an adhesive backing, and then diced into individual die using a diamond edge saw. Using the wafer map that was created in probe, individual die are picked from the wafer, then placed on a circuit board. A solid gold wire is used to connect each chip to the circuit board. A molding process encapsulates each die in a protective plastic package and shipped to test. Every memory chip Micron manufactures undergoes hundreds of tests to ensure it meets the highest quality standards. Proprietary Ambix testers subject finished parts to extreme temperatures and conditions to force any weak components to fail before they reach our customers. Additional test equipment verifies that each part meets or exceeds its speed and performance specifications. All qualified parts are laser marked with part numbers and other identifying information. Each memory chip is optically scanned to verify strict fit and form specifications. Components are placed into industry standard anti-static packaging and placed into boxes for shipment. Many of Micron's finished parts are used to build memory modules and solid-state drives. Automated surface mount assembly equipment is used to mount memory and other components to printed circuit boards. All products are tested using proprietary Micron memory module and SSD test equipment. Finished products are placed into anti-static packaging before boxing for shipment to the customer.
So next one will be the eligibility criteria for VLSI job. So to get a job in VLSI, so what are the qualifications are required? I will discuss here. For the BTech students who are completed their graduation in EEE, ECE, ENTC, EIE with a 60% as a minimum percentage, and anyone VLSI course must be completed. And for the young tech students who are completed their graduation in VLSI, embedded, electronics with a 60% as a minimum percentage, and anyone VLSI course must be completed. So these are the eligibility criteria is there for VLSI jobs. So about Takshila VLSI Technologies. So our institute is the best institute in Bangalore and Hyderabad for freshers and working professional for advanced VLSI studies with 100% placement till you get placed here. So industry standards EDA tools with 24/7 tool support will be there. So whatever the tools we are using nowadays in industry, so that same tools we are using during our lab practice, and faculty and trainers are with minimum 15 plus years of the experience in semiconductor domain. And we are collaborated with 200 plus hiring companies and 100% placement with training material and mock interview will be there, and proven track record of the placements with scholarship facilities. So this is all about the Takshila VLSI technologies. So how to select Takshila VLSI? So Takshila VLSI having some unique features. So unique features are like 100% placement assistant guarantee and 24/7 lab support will be there. So whatever so whenever you want to access the lab, you can access it and you can practice it. And low price will be there compared to another institute, and industry standards course syllabus will be there. So in Takshila Institute, you will get 100% placement assistant, industry standards course curriculum, 24/7 lab support, and low cost value for the money. So these are the unique features are there in Takshila Institute. So infrastructures and labs in Bangalore. So these are the images of the classes, labs and placement cell in Bangalore location. It is also infrastructures and labs in Hyderabad. So we are having Takshila branch in Hyderabad location also. So these are the images of the classes, placement cell in Hyderabad location. So we are having a small video on Takshila VLSI corporate video. So let's see that one. The next one will be the courses offered offline and online. So we are having the both courses for the offline and online students for freshers and working professional. So in Takshila Institute, we mainly provide the 5 courses: physical design, ASIC verification, analog layer design, design for test, and analog circuit design. So these are the courses are there in Takshila Institute. So training methodology and intake. So for the physical design, DFT or ASIC verification, the duration of the course will be 5 months. Daily 2-hour class and lab practice will be there with full-time mentor. And number of the students are 15 to 30. 24/7 VPN lab access will be there. So whenever you want to access the lab, you can access it and you can practice it. And LMS portal access will be there for physical design or DFT and ASIC verification. So what is the meaning of LMS portal means? So here you will get the recorded session of the videos. So whenever you will miss some classes, then you can watch that recorded session. So 50 plus years of the experience, Takshila full-time trainer and full-time mentor will be there. And 100% placement assistant will be there till you get placed here. Analog layer design. For the analog layer design, the duration of the course will be 4 months. Daily 2-hour class and lab practice with full-time mentor will be there. The number of the students are 15 to 25. 24/7 VPN lab access will be there, and LMS portal access will be there. 100% placement assistant will be there. You will get placed here. For the analog circuit design, the duration of the course will be 14 weeks. So it will be the weekend batch. Only 6 hours per week class and lab practice will be there. And number of the students are 10 to 15. 24/7 VPN lab access will be there for this analog circuit design also. Here also you will get 100% placement assisted till you get placed here. So this will be the training methodology and intake will be there in Takshina Institute. So core job opportunities in PD. So after completion of the physical design course, so you may get a job opportunity as physical design engineer. So where the physical design engineer will do the IC design. And you may get a job opportunity as STA engineer. So STA is a part of this physical design where engineers will do the timing analysis. So physical verification engineer. So in this, so whatever the ICs we are formed in this, means whatever the ICs we are designed during this physical design stage, so that will be verified by this physical verification engineers. So EM and IR sign off engineers. So this EM and IR are the issues in this sign off stage. So to reduce these issues, we are having this EM IR sign off engineers and methodology and flow engineers. So these are the core job opportunities are there after completion of this physical design course. So core job opportunities in AMS. So after completion of this analog layout and design course, so you may get a job opportunity as analog layout design engineer, standard cells layout design engineers. Standard cells means, so it includes some NAND gate, OR gate, inverter, buffer. So for particular standard cells, we are designing the layout here. So for input and output layout, layout design engineers means for particular input and output, we are designing the layout here. Memory layout design engineers and RF layout design engineer. So these are the core job opportunities are there after completion of AMS course. So core job opportunities in ASIC means after completion of the ASIC. So this will be the front end. So after completion of this front end means ASIC design and verification course. So you may get a job opportunity as ASIC verification engineer, ASIC or FPGA RTL design engineer, IP verification engineer, and UVM verification engineer. So these are the core job opportunities are there after completion of the ASIC course. The industrial salary scope. So after completion of the VLSI course, so you will get the starting package as 4 to 6 lakhs. So as a fresher, you will get the 4 to 6 lakh as a starting package with a 3+ years of the experience. Means after 3 years, so you will get offer from the product based companies. So with a package of 15 to 20 lakh. So with the 5+ years of the experience. So after 5 years of the experience, so you are there in team lead position with a package of 25 to 30 lakh. So with the 10+ years of the experience, means after 10 years, so you are there in team manager position with a package of 60 to 80 lakh. So this will be the industrial salary scope is there after completion of the VLSI course. So placements at Takshila VLSI. Placement support. So we are tied up with the 200+ hiring companies. So it include product, service, and startup companies. So MNC companies are there like L&T, Capgemini, HCL, Wipro. And here you will get tool and interview support till you get placed here. And you will get 4 to 6 lakh package as a minimum package after completion of the course. So 100% placement assistant will be there till you get placed here. So this will be the placement support will be there in Takshila Institute. So placement process. So this is how Takshila Institute will do the placement of the students. First, we will get the requirement from the clients. After that, we will assist our student for the preparation of the resume. After preparation of the resume, we will send the students' resumes to the clients. So they will shortlist the students and call for the interview. So based on their hiring process, they will conduct the interview. and announce the final result of the selected candidates. So this will be the selection process will be there in so this will be the placement process will be there in Takshila Institute. So here you will get 100% placement guarantee. So gateway for the semiconductor industry Takshila VLSI. So we are tied with the 200 plus hiring companies, including Apeksha, NXP, Broadcom, Insemi, Northchip, Radian, Qualcomm, Central. So these all companies are there with Takshila Institute. So in these all companies, our students are placed and working now. So 2024 placed students. So these are the list of the students who are placed in 2024. So our students are placed as a physical design engineer, analog layout design engineer in the companies like Cadence, XLVLSI and Tessol. So one of our students placed in on semi with the industrial higher salary package as a 20 lakh per annum as an analog layout design engineer. And Abhimanyu Kumar is placed in Synopsys as an analog layout design engineer. And one of our students called Utti Paveshri, she is placed as an analog layout design engineer with the industrial higher salary package as 12 lakh per annum. So these are students who are placed in 2024 in multiple VLSI companies. So you can observe here, so our students are placed in many more VLSI companies. So our students are placed in companies like ARF, TrueChip, Cafet, Agelsia, Digicom, Centaurus, Insights, DPI. So many more companies like Chipwave, Crisemi, Ambit, Maverick, SmartSoft. So in these all companies, our students are placed and working now. You can observe here. So these are the list of the students who are placed in multiple VLSI companies. So along with these students, many more students are there who are placed in multiple VLSI companies and working as a physical design engineer, analog layout design engineer. So in many more companies. So these are the students. So you can observe here. The 2024 placed students company wise. So in Capgemini itself, 13% of the students are placed. So in L&T Technologies, 1.5% of the students are placed. So the many more companies like P2F, HCL, Tessol, Junitron, Centaurus, Digicom, Apeksha. So other companies like Cadence, Silica, Ananta, Blueberry. So in these all companies, our students are placed and working now. So if you want more information of the fees and course, you can directly visit our office, which is there in Bangalore and Hyderabad location, or you can directly contact us through phone, email, or website. After this, we will start some technical part of today's webinar. So it includes analog, means AMS and digital design flow. So we'll start that one. So first will be the type of the ICs. So whatever the type of the IC will be there, so that will be classified as analog and mixed signal ICs and digital ICs. So in analog and mixed signal ICs, so whatever the output will be there, so that will be varying according to time year. For example, you can take simple chips, audio processing, memory, sensor and power. So these sensors are the very good example for this analog and mixed signal ICs. Because so whatever the output will be there, so that will be varying according to time year. So in digital ICs, so whatever the output will be there, so that will be varying at constant 0 and constant 1. So you can take example as complex chip, processor, wireless, USB and Bluetooth controller for the example for this digital ICs. So what is mean by this analog and mixed signal ICs? What is meaning of this digital ICs? We will see in detail in next slides. So analog IC design process steps. So it includes some front-end step and some back-end step. So in front-end step, it includes some analog circuit design. So in back-end step, it includes analog layout design. So what is mean by this analog circuit design? What is meaning of this analog layout design? We will see in detail in next slides. So analog IC design flow. So whatever the analog IC design flow will be there. So that will be include some front end face and some back end face. FE means front end, BE means back end face. So this front end face will be designed by analog circuit design engineers. And these back end face will be designed by analog layout design engineers. So in front end phase, the first step will be the schematic design. So you may ask question, what is the meaning of schematic design then? So whatever the IC will be there, so that whatever the design of the IC will be there, so that will be drawn in the form of the circuit diagram. So how that will be drawn means, so by using the symbol, so you can observe here, so by using the symbols and logical connections. So these are the logical connections. So by using the symbols and logical connections, we are drawing this schematic diagram. So after this schematic diagram, the next step will be the simulation. So what is the meaning of simulation then? Simulation means, so whatever the output of the circuit will be there, so that will be checked based on the input vectors and test vectors. So after the simulation phase, if the specifications are met, then we will move to the next step. Means we will move to the back end phase. So in back end phase, the first step will be the placement and routing. So after this placement and routing stage, you will get the layout of an IC. So this will be the layout of an IC. So after this, we will do the DRC. DRC means design rule check. So what is the meaning of DRC then? DRC means design rule check. So what is the meaning of this design rule check then? So design rule check means, so whenever we are performing IC design, so at that stage, so tool will be provide some rules. So if you are not following that rules in our entire design, then these DRC violations will arise. Means, for example, you can take, if two metal layers are running parallelly, so we should maintain some minimum distance of 1 micrometer. So if you are not maintaining this 1 micrometer distance in our entire design, then minimum spacing DRC violation will arrive. So like this only, the another DRC violations are also there, like minimum area, minimum width, and pitch. So this is all about the DRC. So after DRC, the next step will be the LVS. So what is the meaning of LVS there? LVS means layout versus schematic. Layout versus schematic means, so here we will do the physical comparison between this schematic design and layout design. Means we will check whatever the connections are present in this schematic, we will check that same connections are present in this layout or not. So that will be performed by this LVS. So after that, we will do the parasitic and LDA extraction, post layout netlist simulation. If the specifications are met, then we will get this analog IC design. The next one will be the analog IC design flow. So it includes complete layout and schematic of an op-amp. So this will be the schematic of an op-amp. So this will be the layout of an op-amp. So whatever the schematic design will be there, so that will be formed by using symbols and by using logical connections. So these are the logical connections. So by using these logical connections and symbols only, we will do the schematic design. So this schematic design will be converted into layout by using the metal layers and wires. Means whatever the logical connections are there, so that will be converted into physical connections by using the metal layers and wires here. So this is all about the schematic and layout of an op-amp. So next step will be the digital IC or ASIC design flow. So whatever the digital IC or ASIC design flow will be there, so that includes some front end steps and back end steps. So before that, so you already know what is meant by ASIC, means application specific integrated circuit. So you already know what is the meaning of this ASIC. So it is a digital circuitry which is made up of permanently connected gates and flip-flops in a silicon, so the logical function can't be changed. So what is the meaning of this means? So whatever the gates and flip-flops we are using in our design, so that will be not designed from its scratch. Means already designed flip-flops and already designed gates are present. So that we will directly take and we will directly add into our design. So we will not design from its scratch. So that is the meaning of this sentence. So nowadays ASIC has a complete system on it, often called a system on chip. So what is meant by system on chip means, so in one IC only all the systems are present, like audio processing, video processing, image processing, display. So these all systems are present in one IC only. So because of that purpose we will call it as SOC. So whatever the digital IC process will be there, so that will be include some front end step and some back end step. So in front end step, the first step will be the design specification. So what is the meaning of design specification then? Design specification means, so these are some information which will be collected by marketing team based on the customer requirement. So based on their requirement, we are fabricating the ICs here. So after that, we will do the RTL description. RTL description means, so whatever the RTL code will be there, so that will be written in this stage. Then how we are written that RTL code means, so by using some hardware description languages like Verilog, VHDL and System Verilog. So by using this hardware description languages, we are writing this RTL code. So after that, we will do the functional verification. So whatever the RTL code we have written in this RTL description stage, so that will be verified in this functional verification stage. So then how this RTL code will be verified? So this will be verified by using some test vector, means by applying some test vectors and some input vectors to the code, this RTL code will be verified. So if this RTL code is not containing any errors, then we will move to the next step. So that will be back end step. So in back end step, the first step will be the logical synthesis. So what is mean of this logical synthesis? Means, so whatever the RTL code we have written, so that will be converted into gate level netlist here. So that will be called as logical synthesis. So after this gate level netlist, we will do the logical equivalence check. Logical equivalence check means here we check the consistency in between this RTL code and gate level netlist. Means we will check whatever the connections, nets, wires are present in this RTL code. So that same connection, nets and wires are present in this gate level netlist or not. So after that, we will do the place and route. So in place and route, so it is the step of physical design. So in this step, so we will we'll create the core area, die area. So whatever the macros are there, so that macros will be placed here. We'll place the standard cells. So whatever the logical connections are there, so that we will convert into physical connections by using the metal layers and wires here. So after this place and route stage, the next step will be the physical layout. So you will get the physical layout after this place and route stage. So for this physical layout, we will do the physical verification. So whatever the verifications are there, so that will be performed to the IC. So that will be performed by this physical verification step. So after verifying the IC, we will get some file called as GDS2 file. So this GDS2 file is the ready for the fabrication file. Means whatever the information is needed for the fabrication of the IC, so that will be present in this GDS2 file. So this is all about the digital ASIC design flow. So next step will be the digital ASIC design flow step. So it includes some front end step and some back end step. So in front end step, so we'll write the RTL design, means whatever the RTL code will be there, so that will be written in this RTL design stage. So in ASIC verification, so this RTL code will be verified here. So in DFT, so to test our design, so we are using this DFT stage. So in backend, the first step will be the physical design. So whatever the IC will be there, so that will be designed during this physical design step. So that will be verified in this physical verification step. So what is mean by this front end step? So what is meaning of this back end step? We will see in detail in next slides. So the first step in ASIC design flow will be specification. So what is the meaning of specifications then? Specification means, so chip specification are driven by end customer based on the market requirement. So some of the typical specifications are small size, high speed, low power consumption, or any other new requirement to do the certain function. So what is the meaning of this means? So whatever the specifications are there, so that will be provided by the end customer based on the customer requirement. Means, so if one customer want the IC like small size, high speed and low power consumption, and another customer want like IC like big size, high speed and low power consumption. So based on their requirement, we are fabricating the ICs here. So that will be present in the specification. Means some information will be collected by customer team here. So after the information provided by the specification team, the architecture team will design this architecture design. Then how they are designing this architecture then? So this will be designed in the form of block diagram, flow charts and specification sheets. So based on specification information, so these architecture design will design this block diagram, flow charts and specification. So after this, the next step will be the RTL design stage. So whatever the RTL code will be there, so that will be written in this RTL design stage. So register transfer level means RTL is constructing a digital design using the combinational and sequential circuits. So you already know what is meaning of this combinational circuits and what is meaning of the sequential circuit. So in combinational circuit, so whatever the clock is there, so that will be not provided. For example, you can take multiplexer, encoder, decoder. So in sequential circuit, so whatever the clock is there, so that will be provided to the circuits. For example, you can take flip-flop, latches. So whatever the combination and sequential circuit is there, so by using that combination and sequential circuit only, we are writing this RTL code. So how we are writing this RTL code then? So we are writing this codes by using some languages like Verilog or VHDL. So by using these languages, we are writing this RTL code. So this will be the RTL code. So it includes some model, input, output, and so by using some styles like behavioral style modeling or data flow modeling, we are writing this RTL code here. So if this code includes any sequential circuit, so we should include the clock here because sequential circuit require the clock. So because of that purpose, we are include some clock in this code. So this code will be described how the data is passed from register to register. So we'll get how the data is passed from one register to another register. So by using this code only. So this is all about the RTL design. So whatever the RTL code we are written in the RTL design step, so that will be verified in this RTL verification step. So how they are verified means, so by using some steps like architecture modeling, design specification, functional test plan, and functional verification environment. So whatever the RTL code is there, so that will be verified in this functional verification environment. Then how this RTL code will be verified? So this will be verified by using design under test. So design under test means, so whatever the RTL code will be there, so that will be checked based on the input vectors and test vectors. So after that, we will analyze the circuit. If the expected results are matched, then the ASIC verification will be completed here. So ASIC test environment diagram. So how the ASIC test environment diagram is there means, so that will be divided as test code and test bench. So whatever the code is needed to be tested, so that will be present in this test code. So in test bench, we are included the clock here. So you may ask question, why we are including the clock here? Because if this test code contain any sequential circuit need clock. So because of that purpose, we are including the clock here. So we are including the BFM. BFM means bus for model. So it will be acting between this test code and test page. So to transfer the data between this test code and test bench, we are using this BFM. So unit under test. Unit under test means, so to check this test code, so we are applying some input vectors and test vectors. So that will be there in this unit under test. So it also includes some other modules in test bench. So this is all about the ASIC test environment diagram. So next step will be the design for testability. So I already told these DFT will be used to check our design, means to test our design after the post-production process. So after the post-production process, to test our design, we are using this step. So you may ask question, why we are required to do that post-production process testing? So what is the need of testing that? What is the need after post-production testing? Means, so whatever the process of the manufacturing is there, so whatever the process of the manufacturing is there, so that is not 100% error free. Means whatever the chip we are designing, so that is not 100% error free. So there are some defects are there in silicon. So why these errors will come means, so there are some defects are there in silicon which contributes towards the errors introduced in the physical device. So because of defects in silicon, so there are some errors are there in IC. So because of that purpose, we are testing. So we are doing this post-production testing. So you may ask question, how we are doing this post-production testing? So by using some, means by adding some extra logic to our design. So how we are doing means by adding some extra logic to our design, we are performing this DFT. So what is that extra logic then? So what is the meaning of this extra logic then? So extra logic means we are adding some scan chains here. So what is the meaning of scan chains then? Scan chains means the back-to-back connection of the flip-flops. So you already know the pin of the flip-flop. So it includes some D pin, some ESC pin, some SI pin, some Q output pin, some Q bar output pin. So you already know that one. So whenever this ESC means scan enable pin is equal to 0, at that time all the flip-flops will act in functionality mode. Functionality mode means, so whatever the flip-flops are there, so that will perform some functionalities like reading, writing, and display and storing. Sorry, reading, writing, and storage. So these functionality will be performed by this flip-flop. So that will be called as functionality mode. So whenever SE pin is equal to 1 means whenever scan enable pin is equal to 1, that time all the flip-flops will act in test mode. So what is the meaning of test mode there? Test mode means so whenever this scan enable is equal to 1, at that time the first flip-flop will take the input from the SI pin and it will check the output of the all the flip-flop. So it will check the output of the all the flip-flops in the entire design. So this process will be there. So in this DFT, so this is how DFT will perform the post-production testing. So after DFT, the next step will be the physical design flow in ASIC design. So whatever the physical design is there, so that will be include some steps like partitioning, floor planning, placement, CTS, the routing, and timing closure. So what is the meaning of partitioning there? Partitioning means so whatever the full chip will be there, so that will be divided as sub-block. For each subblock, we are separately performing the floor planning, placement, CTS, signal routing, and timing closure. So that will be there in this partitioning. So what is meant by this floor planning, placement, CTS, signal routing, and timing closure? We'll see in the next slide. So physical design flow. So the design cycle of the VLSI chips consists of different consecutive steps from high level synthesis to the packaging. So you already know the process of the steps of the ASIC design. So it includes the steps from ASIC design to packaging. So like that only the physical design also include the some steps from synthesis to packaging here. So the physical design is the process of transferring the circuit description into physical layout. Means so whatever the logical connections are there, so that will be converted into physical connections by using the metal layers and wires. So that will be there in this physical design. So the main objective of the physical design engineer is to generate a layout with a minimal area. So this will be the main objective of the physical design engineer. Means whenever the engineer will designing one chip, so at that time he should follow some rules like PAP rule. PAP rule means power, area, and performance. So whenever engineer will designing one chip, so at that time, so the chip consists some points like power should be minimal, area should be minimal, performance of the chip should be good. So these points he should consider while designing the chip. So these are the main objective of the physical design engineer whenever he is designing one chip. So next one will be the import design and initial checks. So this will be the first step of the physical design. So here we will collect all the input files. So these are the input file. So these are the input file for the physical design. So we will collect these all input files and we will link these input file to the tool. Tool means the software. So we will link that input file to the tool or library. So that process will be there in this import design step. So whatever the input are required for the physical design then, so the inputs are like gate level netlist, constraint, logical and physical libraries, def file, scan def, and UPF file. So these all files will be these all files will be required for the physical design flow. So why these files will be required for the physical flow then? Because it includes some informations like gate level netlist. For example, you can take the gate level netlist includes some information like it includes macro information. Macros means, so these are the fixed circuit. So that will be that we will get from the vendor. So it will be include some standard cell information. Standard cell means, so these are the cells like, and these are the cells. So it includes some gates like AND gate, OR gate, some inverter buffer, then some flip flops, latches. So that will be included by the standard cell. So it also include the reference name. So what is the meaning of reference name there? Reference name means while designing the chip, tool will provide some name to the cell. So tool itself provides some name to the cells. So that will be called as a reference name. For example, you can take for AND gate. So you already know the AND gate, right? So for this AND gate, tool provides some name like AND 2 X2 HVT. So this will be the reference name for this AND gate. So this will be provided by the tool here. So AND is the name of the gate. 2 is the two inputs. So these are the two inputs. X2 is the drive strength. Drive strength means the capability of this cell to drive the number of the output. So that will be called as drive strength. So it includes flavor like HVT. HVT will be the flavor. So along with this flavor, it also includes some other flavors like RVT and LVT. Means high threshold voltage, medium threshold voltage and low threshold voltage. So these all informations are present in this gate level netlist. So these all information will be provided for the physical design flow. So along with these gate level netlist, we will provide the constraint files to the physical design flow. So this constraint file include clock related information. Why will require this clock related information means, so I already told these standard cells include some flip flops and latches. So these are sequential circuits. That flip flops and latches are sequential circuits. So that will be required clock. So that will be that information will be provided by this constant file. So clock related information means, so what is the input pin for the clock? What is the output pin for the clock? So what is the timing of the clock arrival? So these all informations will be present in this constant file. So these constant file will be given as input for the PD, means PD for tool we are given these constant files. So we also give the logical and physical libraries for the physical design. So this include some timing, area and power information. So that will be included in this physical and logical and physical libraries. So in def file, it include physical information. Physical information means, so I already told these macros and standard cells, right? So where these standard cells and macros are located, so that all information will be provided by this def file. So scan def. So it includes scan chain information. So I already explained about the scan chains in DFT stage. So about this scan chains, so these all informations will be present in the scan def file. So in UPF file, so it include power related information, means whatever the power is required for chip. So what are the cells are belong to each power domain. So that all informations will be provided by this UPF file. So these files we will give as an input for the physical design flow in import design stage. After this import design stage, we will perform the initial checks. Initial checks means, so to check import design is correct or not, means all the files are loaded to our tool, all the files are loaded to physical design tool or not. So to check that one, we will perform this initial checks. So what are the initial checks means? We'll perform check net list. So by check timing, check design. So these are the initial checks we will perform after this import design stage. So to check whether this import design is correct or not, we are performing this initial checks. So after this import design and initial check stage, so this is how layout window will look like after the import design stage. So this will be the die area. So this will be the core area. So whatever the macros I am calling, so these are the macros. So these macros are present in 0, 0 location in import design stage. So these all macros will be added into this core area in floor planning stage. So these are the standard cells. So these standard cells will be added into this core area in placement stage. So whatever the import design is there, so that will be created by sourcing the script. So whenever we will source the script, so whenever we will source the script over tool, so automatically it will create core area, it will create die area. So it will take macros and it will take standard cells. So whenever you source the script, so we will create the scenarios here. So what is the required to create the scenario here means, so our chip must needed to operate in different conditions and different temperature. So because of that, we are creating the scenarios here. So whenever you are execute this start GUI command, so in your tool, so at that time this layout window will automatically open. So this will all about the import design and initial check. So after import design of physical design, so next step will be the floor planning and power planning. So whatever the floor planning and power planning will be there, so that will be divided as full chip floor planning and block level floor planning. So what is the meaning of full chip floor planning then? Full chip floor planning means, so whatever the full chip will be there, so that will be divided as number of sub blocks. So these are the sub blocks. And each block will be perform some different functions like video processing, audio processing, then display, then memory processing. So these all different functions will be performed by different blocks here. And for each sub block, we'll separately perform the block level floor planning. Means for each sub block we are performing the floor planning here. So that will be performed by this block level floor planning. So we are planning the power, we will do the power planning in this full chip floor planning. So what is the meaning of power planning means? So whatever the main power is there, so that will be supplied to each and every sub block equally here. So that will be called as power planning. So in block level floor planning, so in full chip floor planning, we are placing the means whatever the full chip is there, so that will be divided as sub block here. So in block level floor planning, so whatever the chip will be there, so in whatever the block area is there, so in for each block means we will consider one sub block here. For each sub block, we are performing the block level floor planning here. Means so whatever the macros I am calling, so that will be placed in this block level floor planning. So how we are placing this macros means, so deciding on the channel length of the macros means, channel length means whenever you are placing the macros, so we should maintain some minimum distance between the macros. So that will be called as channel length of the macro. So deciding on the halo requirement, then IO code planning will be done, row creation will be done. So row creation means, so whatever the block will be there, so this block will be divided as number of the vertical line and number of the horizontal lines. So this will be called as side rows and side columns. So that will be called as row creation. And power planning is also there in this block level floor planning. Power planning in block level floor planning means, so whatever the main power is there, so that will be supplied to each and every macro equally here. So that will be called as power planning. So in full chip floor planning, so whatever the main power is there, so that will be supplied for each and every sub-block. So in block level floor planning, so whatever the main power is there, so that will be supplied for each and every macros here. So that is the main difference is there in between this full chip floor planning and block level floor planning. So in floor planning and power planning, we are having the core limited design. So what is the meaning of core limited design means? So this will be the estimation of the cores. So we are estimating this core area based on the standard cell area and macro area. So I already told these macros and standard cells we are adding into this core area. So that will be estimated. So that core area will be estimated based on some formula like core area is equal to standard cell area plus macro area divided by utilization. So utilization means the area occupied by the standard cells and macros. So that will be called as utilization. For initially, we are taking utilization as 70%. Means this in this core area, we are taking utilization as 70% and 30% area is left free for the future purpose. Means whatever the 70% area is there, so in that 70% area only we are placing this standard cells and macros, and whatever 30% area is there, so that will be left for future purpose. So that will be there in this core limited design. So this is how layout window will look like after the floor planning and power planning stage. So whatever the macros are present in this 0, 0 location in import design stage, so that will be added into this core area in this floor planning and power planning stage. So these are the standard cells. So these standard cells we are added to this core area in placement stage, and whatever the GUI will be there, so that will be contain some menu bar section, toolbar section, active tool related setting window and layout window. So these are the main sections are there in GUI. So after floor planning and power planning, the next step will be the placement. So I already told in placement, we are adding all the standard cells into the core area. So what is meaning of placement means? So all the standard cells are added into the core area exactly on side rows and side columns without any overlap. So I already told what is meant by side rows and side column. So on that side rows and side columns only, we are exactly placing these standard cells. So that process will be there in this placement. So how we are placing these all the standard cells exactly on side rows and square columns then? So by using some formula. So the main formula are like initial placement, legalization, and place off. So whenever we are executing these three commands in your tool, then all the standard cells are placed exactly on the side rows and side columns without any overlap here. So we are placing also based on the IO port communication. The main issue in the placement stage are timing and congestion issues. So these are the main issues in the placement stage. So to reduce that one, we are given some placement constraint here. Then all the cells are aligned to needed to align in placement grid. So what is the meaning of this needed to be aligned to placement grid means? So whatever the block area is there, We already told. So this block area is divided into number of the side, number of the horizontal and vertical lines that are called as side rows and side columns. So whenever you are placing the standard cells, so all standard cells are placed exactly on this side rows and side columns. So this will be called as legal placement. If you are not placing the standard cells exactly on the side rows and side column, this will be called as illegal placement here. So this will be called as aligned to placement grid. So the main goals of the placement stage are like place utilization jump, no congestion, no overlap, and good timing values. So these are the main goals of the placement stage. So this is how layout window will look like after the placement stage. So whatever the standard cells are present in this location in previous stages, so that all standard cells we will add into this core area in this placement stage. So to do the placement, so to place the all the standard cells exactly on the side rows and side columns, we are adding the script, means we are sourcing the script. So whenever source the script to tool, so automatically all the standard cells will be added into the core area. So after the placement stage, the next step will be the CTS, means clock tree synthesis. So whatever the clock is there, so that will be built in this CTS step. So you may ask question, why will require to build the clock here? Because I already told in placement stage we are adding the standard cells. So these standard cells will be having some flip-flops and latches. So for flip-flops and latches we will require the clock, right? So that will be built in the CTS step. So how that will be built means, so whatever the main clock will be there, so that will be built by using the create clock command. So whenever you are executing this create clock command, the main clock will be built, and this main clock will be supplied to each and every sequential circuit equally here. So how we are supplying this means, so by following some methods. So the main methods are like clock tree, clock mesh, and clock spine. So by using these methods only, we are supplying main clock to each and every sequential circuit here. So you can take example clock tree. So in clock tree, whatever the main clock is there, so that will be divided as sub clock here. So we'll divide the sub clock up to we'll get leaf cell. So these are the leaf cells. So you may ask question, only one metal layer is enough to do the connection from this main clock to leaf cell. So why we are using multiple here? Because if the metal length is too long, it will provide some resistance. Because of that, voltage will be dropped here. So because of that reason only, we are using some clock buffers and clock inverters whenever we are performing this clock tree. So to do the CTS, we are defining some routing rules. The main routing rules are like double spacing and double width. So what is mean by this double spacing? What is mean by this double width? You will get when you will take the PD course, and we will define the target instruction delay and target skew values. We will define the clock cells to use. So whatever the cells are used while performing the CTS, so that will be defined in this step, and defining the routing layers to use. So whatever the layers are used for building this clock tree, so that will be defining this defined routing layers. So whatever the CTS and optimization of the CTS will be there, so that will be performed whenever we will source these two scripts. So after sourcing these two scripts, automatically tool will perform this CTS and optimization of the CTS. So the next step will be the routing. So what is the meaning of routing means? So before this routing stage, so whatever the connections are there, like the connection between the standard cells to port, standard cells to macros, macros to macros. So these all connections are logical connections. Logical connections means we are not perform any real connections. Means these connections are by using wires and nets. So by using nets and wires, we will do the connections between the macros and standard cells. So after routing stage, so whatever the logical connections are there, so that we will convert into real connections or physical connections by using the metal layers and wires. Means whatever the wires or nets are there, so that will be replaced by metals and wires here. So how they are replaced means, so by executing some 4 steps like global routing, track assignment, detailed routing, search and repair. So after executing these 4 steps, all the metal layers and all the logical connections are converted into physical connections here. So what is meaning of this 4 step you will get when you will take the PD course. So this is how layout window will look like after the routing stage. So in routing stage, we will do the pre-route check. So whenever you execute check Zadati routability command, so after executing this command, you will get some errors like number of out of boundary ports, number of minimum grid error, number of block ports. So we should mention these all errors and we should clear these all errors. Then only we will move to the next step. So to do the to do the routing, we will source the script only. So after sourcing the script, so whatever the logical connections are there, so that will be converted into physical connections. So after routing stage, the next step will be the physical design verification or sign off step. So this will be the last step of the physical design flow. So here we will perform some type of the checks. So the main types are like formality check, the LVS check, DRC, timing analysis, design rule violation, IRDOP analysis. So in formality step, we will we will do the checks related to design. Means check netlist, check design, then check utilization, check congestion. So these all checks will be performed in this formality check. So in LVS, we'll check some issues like opens and shorts. So these issues will be performed in this LVS step. So in DRC, we will check metal and wire related issues. So any issues are there related to this metals and wires, so that will be executed after checking this DRC violation. So in timing analysis, we'll check the setup and hold. So in design rule violation, we'll check the max trans, means maximum transition, and max gap, means maximum capacity. So these checks will be there in this design rule violation. So in higher drop analysis, so what is the meaning of higher drop means? So when the metal length is too long, it will provide some resistance. So because of that, voltage will be drop here. So the drop in voltage in this metal layer is called as iron drop. So we will check all these errors. So we'll check these all the errors in the sign off stage. So after so if you are not checking these all the errors, then you are not clearing this all the errors, and you are directly moving to the next step. Means it may damage your IC in future. So because of that purpose, we are performing these all the checks in this physical design verification or sign off stage. So I did from my side. So if you have any questions, means you can ask. Yes, students, if you have any questions regarding technical parts and non-technical parts, you can ask. If you don't have any questions, means I will end up the today's webinar. Thank you.
Hello everyone, a very good afternoon. A heartful thanks to our speaker Rohini ma'am for sharing their valuable insights. I would also like to thank the HOD and students for their efforts in making this webinar a success. Looking forward more such interactions. Thank you all.